Hey everyone, for the chapter review stations, chapter 5 review stations, and these stations cover the whole chapter, I thought I'd have this cool challenge of working around this amazing reflection from the camera light up there. Yes, I did try turning it off, and wow, what a dark, ancient sepia yellow the video became. So I think I'm going to go with this for now. All right, station one. Station one says a rectangle has its base on the x-axis and upper vertices on the parabola 8 minus x squared. So here's a parabola. Here's 0 to 8. Here's square root of 8. Here's negative square root of 8. And then we're going and building a rectangle. Now, there's lots of different rectangles we can draw in here. We could draw a little tall, thin one, and a little long one. There's an infinite number of rectangles that can be inscribed inside of here. And what we want to know is what's the biggest, what's the one with the largest area. And we also want to know the dimensions of that rectangle. So I'm going to start by drawing this rectangle, and see this point here, I'm going to give it a name. I'm going to call it random point xy. Okay? So let's have that conversation. What is it that we're trying to maximize? We're trying to maximize area. So area is length times width. Well, if this is x and this is y, then I can say that area equals an x plus an x, or two x's, times a y. Now, I'd really like area to be in terms of one variable. And right now, we don't have one variable. We've got two here. We've got x's and y's. So, anything we can do about that? Do we have a helping equation here somewhere? Yes, actually, we do have a helping equation. Remember, they said that this was called y equals 8 minus x squared. Well, how convenient. They gave us the helping equation already written. So a is going to be 2x times 8 minus x squared, or a is going to be negative 2x to the third plus 16x. So I'm looking for when area is greatest, which means I want to consider the derivative of a with respect to x. So a prime is going to be negative 6x squared plus 16. Now, this polynomial is never undefined. And but instead of thinking about setting the derivative to find out when the derivative is undefined, I'm going to start just with finding when the derivative equals 0. So I've got 6x squared equals 16, or x squared equals 16 over 6, or 8 over 3. And then I'm going to take the square root of both sides, and I'm going to get x equals plus and minus 8 thirds, which feels a little uncomfortable to work with. However, it does make me see that this is a little smaller than 9 thirds, which is 3, and definitely bigger than 6 thirds, which is 2. So this is a number between 2 and 3 here, just to help me sort of with the graphing process. Okay, and here, square root of 8. Square root of 8 is just less than square root of 9. So I'm thinking that we've got a complete picture quite accurately looking at this one. Negative, I think since my dimensions are going to be x times 2, I'm only going to be looking at positive values. So what do we have here? Well, I want to confirm that there is in fact a maximum. By the way, there are some implied endpoints here. There's one here at 0, because we're not doing negative sides to a rectangle. And here, we have square root of 8, right? We can't have an x value over here because that's past this bounding curve. So our values are here now. 8 thirds. For the purposes of testing, uh, I'm going to use in A prime, I'm going to use 1, in which case I get positive. Um, this is 8 thirds, this would be 24 thirds, I could do 16 thirds. Oh, 9 thirds. Oh, I see, yes, I can do square root of 9 thirds here. That isn't that something. So, if I have square root of 3, square root of 3 squared is 3, and 3 times negative 6 is negative 18, plus 16 is negative 3. So, yes, I have confirmation that I have a max there. Now, let's make sure we answer the questions that we're being asked. And remember that every time we find a max or a min or any question, we have to write a justification. So let's find out dimensions and area. Here's a nice way to find dimensions because we've already got everything in terms of one variable. So 2 times square root of 8 thirds times 8 minus square root of 8 thirds squared. So that's going to be 8 minus 8 thirds. This, I could write it as 2 root 2 thirds. I'm going to split that into 2. Square root of 8 and square root of 3 times 24 thirds times 8 thirds is 16 thirds. Here, when I rationalize 3 over 3, I'm going to have 2, that's another 2, I'll just write it up. This is going to be 2 times 3 all over 3 times 3 is 3, 16 thirds. Okay, so what do we have? Well, I'm going to get the 2 out, so I'm going to have 4 root 6 times 16 over 9, or 64 root 6 over 9. That appears to be my greatest area. And then do I have the dimensions? Well, remember the dimensions are here. We've got our x value, but we owe the dimensions 2 times x. Okay, so we said that x was equal to root 8 thirds. And so 2x, the length of that rectangle, would be 2 root 8 thirds. And yes, I could write this as 4 root 6 over 3, but I don't feel like that's any tidier or nicer than just leaving it as square root of 8 thirds. Okay, so I've got this, and that's one of the dimensions, that's the length of the rectangle. Now we need this one, which is 8 minus x squared. So that's the 8 minus root 8 thirds squared, or 8 minus 8 thirds, which is going to be 16 thirds. Alright, so then let's go for our justification sentence, since we have to put everything into one sentence. The maximum area of, and somehow this just doesn't feel right, 64 root 6 over 9 units squared occurs when x equals square root of 8 thirds. I want that when, with dimensions of 4 root 6 over 3 by 16 thirds, because to the left of x equals square root of 8 thirds, a prime is greater than 0, and to the right of x equals square root of 8 thirds, a prime is less than 0. Ta-da! There. You didn't think we could get it all in one sentence. And I wasn't prepared. Alright, so there's station 1. Station 2. What are the dimensions of the lightest open-topped right circular cylinder whose volume is 2000? I know. Don't you want to read that one again? What are the dimensions of the lightest open-topped right circular cylinder? It says right so that we don't think the cylinder is doing this kind of thing. And I know you're saying, why would you want that? Well, we don't want that, and that's why we're telling you we want this. And by the way, ours does not have a top. Lightest. So lightest is all about surface area, i.e. if I had to construct this thing, I had to construct this thing out of a material with uniform thickness. The lightest one of these cylinders would be the one that uses the least material and therefore the smallest surface area. Now, for us, because we're super cool and we remember our geometry, we know that the bottom, being a circle, has an area of pi r squared. We also know the side here, if we cut it and unroll it, forms a rectangle. This is the height of that. I erased my. I wondered how long it would take before I could get to that place where I would erase, and it turns out just one problem. Okay, so that's height, and then this stuff. Well, this is this, and so that's circumference, or 2 pi r. So this is 2 pi r h as an area, length times width. And you probably know that. Okay. So then if I'm thinking about, and normally I would have this top, but we were told that ours is open topped. So my surface area formula is simply going to be pi r squared plus 2 pi r h. I do want to, no, I don't want to. Okay, so let's find a prime. Oh, but wait. I got 2 variables here. I don't want area in terms of 2 variables. Do I have a helping equation somewhere? I remember with these optimization problems that having a helping equation could allow me to, say, get rid of h and have area only in terms of r. So let's take a look. Oh, look, volume is 2,000 cubic centimeters. So the volume of the cylinder is pi r squared h. And they're telling me that the volume is 2,000. Okay, good. Oh, I'm just a caution. Okay, not 20,000, but 2,000 equals pi r squared h. And I want to get rid of this h over here. I'm going to divide everywhere by pi r squared. Isn't that interesting? The height is the volume divided by the area of the circle. So I'm going to plug that volume divided by the area of the circle in here. A equals pi r squared plus 2 pi r times 2,000 over pi r squared. And I see that I can cancel a pi, and that I can cancel an r. And so now I've got that area is pi r squared plus 4,000 over r. So when I go to take the derivative of this, I get that 2 pi equals 2 pi r. Now think of this, or I like to think of this because it's much easier on my brain, as 4,000 r to the negative 1. So I'll bring down a negative 1. and I subtract 1, like that. Oh, that's going to mean that this is over r squared. Fabulous. So now I know that the area derivative is undefined when r equals 0, and that should make sense to me. It's not much of a um, a circle if r equals 0. So I would just set a prime equal to 0. So 2 pi r minus 4,000 over r squared. Let's add 4,000 over r squared to both sides. So we have 2 pi r equals 4,000 over r squared. And then I'm going to multiply both sides by r squared. So I'm at this place where it says 2 pi r to the third equals 4,000. And if I want to get r by itself, I better divide by 2 pi. And so I get r to the third equals 2,000 over pi. And we want r, so that's going to be the cube, not the square root. Cube root of 2,000 over pi. Great. Well, this is definitely calculator time for me. I want 2,000 raised to the 1/3 power. Oh, what am I? Silly you. Second insert of parentheses there. Second insert divided by. Okay, and I get 8.602 pi. So let's put that on our area prime number line. The least amount is 0. We can have a negative amount of area. Here's our 8.603. So let's choose a number on either side of that in, remember, a prime. So if I choose 1, because I like dividing 4,000 by 1 as opposed to other numbers like 9. So that's going to be negative 4,000. And over here I have 2 pi, which is approximately 6.28. So 6.28 minus 4,000, yeah, I think that's negative. Negative there. And then over here, if I pick something like 10, because 10 squared is 100, I can take out 2 of those zeros. And 10 over here would be 20 pi. 20 pi. And remember, pi is like this number, a little bigger than 6. So this is around 60. So I've got 60 minus, and remember, this was going to be done from 40. So yeah, it's going to be positive over there. So definitely have minimum occur when r is 8.603. Yeah, that's what the answer says. And what are the dimensions of this? It doesn't ask me to find anything but, I don't have to find total surface area, just to find what the dimensions are. We've got our radius here. Remember we had that height equation? That height was equal to 2,000 over pi r squared. Okay, so I'm going to plug in this 8.602 number. Actually, I'm going to use its unrounded friend here. It's unrounded. I want the true identity for my radius. So I'm going to square that number. And I'm going to multiply that number times pi. And I'm going to take 4,000. 4,000. No, I'm going to take 2,000. Divide 2,000 by that. The magic of the universe. So, when the height and radius are the same. Okay, so let's write us an answer and say the surface area is east. And if you're uncomfortable with that, say the can is lightest or the cylinder is tightest. equals h equals 8.605. I guess you could certainly say p, because to the left of r equals 8.603, a prime was less than 0. To the right of r equals 8.603, a prime is greater than 0. Make sure with this problem that you do give them the dimensions. You have to talk about what h is that explicitly asks for that. Okay? All right, that was station 2. Station 3. United States Post Office. Oh, this is that problem. Goodness, we've seen this problem so many times in the last 2 years. It should be a good friend by now. So please stop ignoring it. For an express y. X, remember, girth is the perimeter of the cross sections of that 4x plus length is 110. Okay? And we want the largest possible volume. The volume of the box is length times width times height. And I get a squared y. Oh no, I have volume in terms of 2 variables. If only I could get volume in terms of only 1 variable. Sure, I need to find out what y is. Do I have a handy helping equation I could use to get rid of y? Why, here it is. And so if I solve this equation for y, 110 minus 4x equals y, I can then replace this y with 110 minus 4x. So volume is going to be x squared 110 minus 4x. Now, by the way, I find it useful at this point to graph v. We've got a negative 4x to the third, so I'm coming down. I'm bouncing at 0 because I have a multiplicity of 2, and I'm passing through here. Where does this intersect? Well, it's 110 divided by 4, which is 55 divided by 2, over 2. Okay. But I don't know where the maximum volume is. I can see it here. But that's clearly going to occur between 0 and this number. Yeah, so let's find the derivative. For the purposes of finding the derivative, I don't want factored form because I don't have the product rule. Instead, I'm going to use the distributed out form plus 1 x squared. So then b prime is going to be negative 12x squared plus 220x. Okay, so let's factor out something. How about a 4x? How about a negative 4x? And so I'm left with 3x minus 220 divided by 4 is going to get me 55. So yeah, 200 and 1. So what do we know? Well, b prime equals 0 when x equals 0, right? Because I have a 0 slope there. But this is the one I'm looking for, and that's 55 over 3. X equals 55 over 3. So my b prime sign chart, it's pretty close to that orbital circle of reflection. B prime, 0 here. This one is 55 over 2, and this one is 55 over 3. And so if I test some values here, like 1. Remember, we're plugging them into v prime, not v, but v prime. If I plug in a 1 here, 3 minus 55 becomes 52, times a negative here. Times a negative here, that's going to be minus, better than 1. So that's going to be negative 4, and 1 is going to be negative 52. So that's definitely a positive number. And if I plug in a number between these, well, I really want to say that a number between these would be 55 over 2.5, but I don't feel comfortable doing that in my head. I gotta say, I'm very comfortable with that. 3 goes into this 1, with 25, that's 8. And so I'll have a little left over. So this is a little bigger than 18, but it's not yet 19, so I'm really cool. So that's going to be 20 times 2 is 60. 60 minus 65 is positive 5. And then 20 here I have negative 80, so negative times positive is negative. Alright, and what are they asking for here? Um, they're asking for what are the dimensions that give the largest possible volume. Well, so now we have our x value that produces our maximum value. What about the y value? So here we go. Remember, we have this equation called y equals that helped us earlier, and it's going to help us now because we want to know what the y value is. We want to know what this dimension is on this box. And we're told that 110 minus 4 times 55 thirds will do the trick for us. Now, sadly, there's no answer. So I guess I could guess the but no, I'm going to take it a little further and say that y equals 110 minus 20 over 3, and then I'll make a common denominator, 30 minus 20 over 3, or 110 over 3. Oh, look at that, double. So volume is maximized when x equals 55 thirds and y equals 110 thirds. Yeah. Thirds, because to the left of x equals 55 thirds, u prime is 3 to the 0, and to the right of x equals 55 thirds, u prime is x equals 0. Ta-da! Okay. So station 4, we're not doing part C because it talks about Newton's method, but we can do parts A and B. Station 4. Station 4 says, here's an f of x. It's ln of x plus 1. And we know that there's a vertical asymptotic of 1, and our graph does something like that. Okay, we shifted our graph 1 to the left, or our ln 1 to the left. And what are we thinking about here? Oh, final linearization of the origin. So remember, linearization is the tangent line. Synonym for tangent. I mean, it isn't. It's zooming in and seeing what that curve looks like when we zoom in so close that we're looking at a straight line. But for all intents and purposes, that's exactly it. So what do we need for a tangent line? We need a point and this one. Okay, well, they gave us the x-coordinate here. You can see from our graph, or if we put a 0 in here, the ln of 1 is in fact 0. Okay, and how do we know the ln of 1 is 0? Well, remember our reference graph here for ln of x. This goes 1 over e negative 1. Well, what was this one? Yes, it was 1, 0. So when I plug a 1 into ln, I get a 0. ln of 1 is 0. Alright, so we know that's our point, and what about our slope? Well, I need f prime. F prime is going to be 1 over x plus 1. And I want to evaluate f prime at 0. I get 1 over 0 plus 1, or 1. So slope is 1. So my linearization, y equals 4. 1 minus 0 equals 1 times x minus 0. And you know what? That's looking a whole lot like y equals x. So there's my tangent line equation. Great, we did that. Now they want us to determine L of A plus 0.01 and F of A plus 0.01. Remember, this A is the specific x value that we're working with in our problem. And our specific x value is here. So I'm going to put 0 here. I'm going to put 0 here. And so what that really means is I want to evaluate L of 0.01. And I want to evaluate F of 0.01. So let's go about evaluating those two things so that we can compare them. So if I want, okay, if I want F of 0.01, F of 0.01, that means I'm going to have the ln of 0.01 plus 1. And I don't know what the ln of 1.01 is. And I know my ln graph. And here's the ln of 1. Well, what's the y value right there? Some small positive number. But I'm definitely going to have to apply the calculator to figure out that one. ln of 1.01. And I get 0.0095. That's my ln of 1.01. But that's our f of a plus 0.01. Now what about our L? Well, remember, this is our L. This is the linearization here. And it's just plug in that number. Well, that number, 0.01, goes in there. And so I'm looking at 101. And that's our equation. Y is x. That's our L of x. And so look how close these are. Tenths, hundreds, thousands, 10,000s, 100,000s. These answers are 2, 3, 500,000 of each other. That's pretty close. I mean, goodness me. Okay, so that's it for there. Don't worry about Newton's method. It's sad. It's Newton's method. It's a hoot. But no, we don't need it on the AP exam. And so we're moving on. Okay, so station 5 says, find the change in the radius of a circle if its area is measured as 2 pi. And we want the change in the radius. Change in radius. Well, remember the change in radius is the differential dr. And we're talking about area here. Area of circle. Pi r squared. And our area is 2 pi. 2 pi squared. Oops. Divide both sides by pi so we can't forget about pi. Q equals r squared. R equals square root of 2. Okay. So this is, I don't know if I'm going to read this. Helps if you read the problem. Find the change in the radius. Find the change in the radius. Find dr. Oh, this must be a differentials question. Find dr with an area. Ooh, notice that last sentence there. The area is measured as 2 pi. The area is measured in 2 pi with an error of 0.01. What has that error? Area has the error of 0.01. That tells me that dA equals 0.01. Okay. So let's see what we can do here. Remember that area is pi r squared. And we want dA dr, which is going to be 2 pi r. And so dA equals 2 pi r dr. And what are we looking for? We're looking for dr. Find the change in the radius. Well, we've got dA. That was given to us. And we have r because we solved for it. So I got 0.01 equals 2 pi square root of 2r. So if I divide by 2 root 2 pi, and I'm going to stop there. And here's my sentence. I'm not going to simplify that. I mean, I will, because most of you know, but go to the parentheses and bulk stuff in the top. 2, 3, square root of 2 times 5 plus close. And I get R is approximately 0.00125 or 0.001. Alright, so my change in radius is approximately 0.001 centimeters. Because remember, our change in area was given as centimeters squared. Okay, 2. Given that y equals x squared x equals 1 with dx equals 0.01, find the differential dy. Well, we know that dy dx requires the product rule here, 2x and x plus x squared times the derivative of ln is that. So we've got 2x and x plus x. This and no, I'm not saying it's equal. This isn't an optimization problem. This is just me now going to multiply both sides by delta x. So y equals 2x and x plus x times dx. And we know that x is 1, and we know the x is 0.1. So 2 times 1 ln of 1 plus 1 times 0.1. Well, look, the ln of 1 we just talked about. We know the ln of 1 is 0. 0 times 2 is 0. 0 plus 1 is going to be 1. 1 times 0.01 is 21. And I'm not given any units here in the second problem, so I'm just writing that and moving on. Okay, station 6. Station 6, water runs into a conical tank, 9 cubic feet per minute. Now, when I think about naming these units calculously, this is volume, this is time, so this must be dV that I'm looking at here. An inverted tank has a height of 10 and a radius of 5. How fast is the water level rising when h equals 6? And how fast is the water level rising? Well, that's a change in this. That's a change in dH. How fast is the water level rising? Okay. Well, I have dV dt. dH dt. We want what's the height, the change in height with respect to time, because time is the thing that's moving things along. So I'm looking for dH dt. I've been given dV dt. Do we have an equation, formula, something that relates volume with height that I can take the derivative of? And yes, the answer is I can take the derivative of volume with respect to height. Okay, so volume is 1/3 pi r squared h. And this time, I'm going to get rid of the r because I'm looking for dH dt. So, only a open equation, none was given to me here. So, this is r, and this is h, and this is 5, and this is 10. So, I've got similar triangles here. R is to h as 5 is to 10, which means that 10r equals 5h. And remember, we're looking to get rid of r this time, not h. So r equals 5h over 10, and I prefer 1/2 h. So where I see r in this volume equation, I'm going to replace r with 1/2 h. So that v equals 1/3 pi 1/2 h squared times h. So that's going to be pi over 3 times h squared over 4 times h. and that's pi over 12 h to the third. So my volume formula is V equals pi over 12 h to the third. Finding the derivative of this with respect to time will be dv dt equals, don't forget to bring down that 3, and 3 cancels here, so pi over 4 h squared, and don't forget the dh dt, because that's the thing you're looking for. Many students forget that we're taking the derivative in this problem with respect to time. So, yeah, we've got to have the change in volume with respect to time and the change in height with respect to time. So what do we know? We know dv dt is 9, we've got 4, and we've got when height is 6. So we've got 6 squared. So that's going to be 36 over 4. And 36 over 4 is, anyway, 5. Don't lose that, what I just did. So I've got 9 pi h dt equals 9, 5 by 9, 5. I get 1 over pi is dh dt. Do they ask me to find anything else? No. How fast is the water level rising? And I guess because this is cubic feet per minute, this would be feet. That's a lot. Fabulous. Yay, related rates. Okay, 7. Station 7. Station 7. Ooh, it's got 2 parts to it. A 20-foot ladder leans against a house. So 20 parts. 5-foot ladder leans against a house. The base starts to slide out. By the time the base is a change in quantities. So keep on 24, the base is moving. dv dt, the change in the base is 7. How fast is the top of the ladder sliding down? And so if we call this height, then I'm looking for the change in height with respect to time. That's the first thing they ask us. How fast is the top of the ladder sliding down the wall at that moment? Okay, so I'm trying to find that. I've got that, and I'm thinking that surely there's some sort of equation, formula that will allow me to relate these things together. And some students say tangent. It's a great idea, except that I don't know anything about this thing. We do have something with this hypotenuse. Do you have any formulas that you're familiar with that relate the hypotenuse with these 2 quantities? And certainly the Pythagorean theorem comes to mind. So d squared plus h squared is 5. We're looking for the h dt, so I want to keep this h showing up, and I want to get rid of these. So I'm going to solve this. Oh, do I want to do that? You know what? I'm just going to shut up and do the problem, because I think this is in fact what I want to take the derivative of. This is the equation that relates all of these things. Sorry about that. So I take the derivative here with respect to time. I take the derivative of the outside squaring function, I leave the inside alone, and now I come back and I take the derivative of that inside with respect to time. Plus, I take the derivative of this outside function, I leave the inside alone, but I have to come back and take the derivative of that inside with respect to time. Now, here's where a lot of people screw up. Say that the derivative of 25 is some number that's not 0. But no, really, this is a horizontal line. This horizontal line always has this label at 0. So I'm putting a 0 there. Now, I'm looking for this, which means I must know this, and this. Well, they did tell me that b was going to be 24. And they told me that dv dt, the change in the base, is 7, plus 2h dh dt equals 0. Well, here's the thing. I'm looking for this, which must mean I know this.